Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully you guys are doing well. Let's actually jump into it because we have a lot of stuff planned for today. Well, not a lot of stuff, but stuff planned that would take some time. So, again, I'd appreciate it if you can turn your cameras on. That would be cool. Just to get a little more personal here. All right, some announcements before we begin. Remember going back to the first class, there were 4 ways I tried to communicate with you guys from my Fordham email, from Jupyter, from Gradescope, from Blackboard. Okay, so I asked you guys, did everyone receive communications from all these avenues? And pretty much everyone received it from my email, but not everyone got it from the others. So you were supposed to email me telling me, oh, Jhevon, I didn't get an email from that. Now, I responded to some people, but not everyone, because over this week, I've been getting a lot of new students as well. And so I don't want to be updating new students with students that were already in my roster. I didn't want to get confused. So I decided I was going to wait a couple days and then just update everyone all together. So if you did email me, just assume I got it, but I'm not really going to wrap things up until over the weekend. So definitely if you don't hear from me by Monday, you can shoot me another email because I probably missed yours. But otherwise, until then, just assume that I found I got your message and I will update it soon. If you did not email me, then you should, as well as I don't think there's anyone new in this class, but if you are new in this class, which means you probably didn't email me, then you should also email me and let me know, oh, I'm new to the class, I joined so-and-so, and just let me be aware of that. Because it turns out that when someone joins new to the class, I don't get like a notification. I should tell them to make that a thing. Like I don't get a notification. Like if the student doesn't reach out to me, or I don't happen to go back and look at my roster in my Fordham, like I wouldn't know. So you should email me if you're new and let me know that you're new, and then we'll get things up to speed. Yeah, I think that's that. And I did want to put this note here. Last time, I remember you guys are a little bit more shy than my other class. And I just wanted to kind of do a public service announcement about that and let you guys know, while there's nothing wrong with being shy as a person, there's nothing morally wrong or anything like that, but there are situations in which being shy can put you at a disadvantage. It can hurt you. And it turns out in the classroom is one of those situations. So I really encourage you guys to engage and answer questions when I ask them verbally if you can. If not, you can put it in the chat. That's something. I'm monitoring the chat as well. But especially if I'm writing, you should say something, because I'm not going to see it if I'm looking down. Yeah, just engage. And a lot of times we're afraid to show ignorance, not just you guys, all human beings. So you might not want to respond if you don't know the answer, or you're not sure if you know the answer. But in that situation, it's sometimes even more important for you to respond, because if there's something that's being lost, I would like to know so that I can address it. And it's better that I address it now, as opposed to it showing up on a test and you don't know how to handle it at that point, and then it actually counts. The stakes are higher. It's better that we handle everything in this low stakes environment. I don't expect you guys to know everything. It's okay to not know the answer. Not everyone knows everything, I promise you. So yeah, let me know what you're thinking or what you're guessing, whether you're sure, you're not sure. So either way, whether you know the answer or you don't know the answer, I really encourage you to engage, because the opposite is also true. There are sometimes that students can sit there and they think they know the answer, but when they say, oh yeah, it's this, right? And I'm like, no, it's not that. So what happens in that situation? That's the situation students get in when they would they feel very comfortable in a class, like they got everything, and then they get the test back and they're like, what's going on? I don't understand, professor. I really understand what's going on in class. Like I guess I'm just bad at tests or I have test anxiety. But no, while that is possible, it is very rarely actually the case. It's just that the student was sure of things that just weren't true, and they didn't realize this because they never actually voiced that opinion to anybody, and they were never corrected. So please, it might be difficult, but please just make the effort. It's actually way more important to do that in an online class than it is in an in-person class. But I would also highly recommend it in an in-person class as well, believe it or not. But it's super more important now. That being said, let's actually continue. We're going to jump right in. Last time, we looked at exponents, exponential rules, laws of exponents, right? So we looked at the laws of exponents, reviewed those. We looked at the graphs. We discussed the difference between an exponential and a polynomial. We're actually going to expand on this fact a little bit more later. And basically the idea is exponentials win, right? If an exponential and a polynomial are fighting, the exponential is going to win, right? Under certain conditions, right? If they're the same kind. Exponentials will increase faster than other increasing polynomials. They will decrease faster than other decreasing polynomials. And sometimes it takes a while for you to notice this. In the short term, you might not notice much of a difference, but in the long term, it gets crazy. We also looked at an example of compound interest. Please be aware that I actually altered the notes here because the way I did it last time, I think I wrote a 3 here when it should have been a 2 or something. I made a typo somewhere in this example and I fixed it. So be sure to fix that on your notes. It has been corrected on the notes that I posted with the video lecture for last class. So you can check those notes and you will see the corrections. So we talked about compound interest and compared that to linear growth, and we kind of ended there. Now, we kind of want to expand on this. So a lot of times we're going to see things in this class like present value and future value because there are two perspectives that are very important. Yes, there's this perspective that, oh, we're planning based on what's going on now, but there's also a perspective where we need to plan for what's going to be in the future. And so that means that we need to be able to look at equations from two different angles. So yes, if I know I have this much money now and I'm gaining this interest rate, then I can tell you after some time, I will have this amount of money. But sometimes the opposite concern is true. Sometimes it's like, I have this amount of money now, I want this amount of money in the future. What is the interest rate and how long should I put it at that interest rate in order to get that in the future, right? So sometimes calculating the A is not the important part. Sometimes calculating the T is going to be the important part. Under these conditions, how long before I get to a certain desired outcome, right? Now, when you want to solve for the T, this is called changing the subject of the formula. This is going to require you undoing the exponential operation, right? So it's kind of like if you had x plus 3 equals 5, solve for x. Well, you know that there's a plus 3 being attached to the x, you have to get rid of it, right? So what do? You do the inverse operation. You subtract the 3, right? So you know, whenever I say addition and I want to get rid of it, I use subtraction. So we are now going to answer a similar question, the analogous question. When I see an exponentiation, how do I get rid of it in order to get to the variable here, right? Sometimes that's the important variable. And this leads us to the other topic, which is called logarithms. So that brings us here. So we're going to talk about logarithms. We're also going to talk about the natural exponential. Maybe I'll switch things up. I spoke about this before that in my other class because I actually had technical difficulties earlier and my brain just got scrambled. But let's do it in a more logical way this time. So let's talk first about the natural exponential. exponential function in math. I'll make a comment about that. So this is called the natural exponential. Okay, this is the function y equals e to the x. Now you may have remembered, oh, I thought an exponential is when the base is a constant. The base is a constant. E is a constant. Like pi, right? So it's like when you write the symbol pi, yeah, technically it's a letter, it's a Greek letter, but everyone knows it represents a number. So you write pi, yeah, it's 3.14159, et cetera, right? Same thing with E. E is a symbol that we use to represent a certain number. We'll see this number again in chapter 3 and probably beyond, but it's a very important number. E is roughly 2.71828. 1 dot dot dot. This is it's a non-repeating decimal. And it is named for Euler, a Swiss mathematician. Chances are, if you have any friends in the sciences, especially biology, you'll often hear them talking about Euler. I'm using Euler's method. Yeah, no, it's Euler. It's pronounced Euler because it's Swiss. Yeah, very prolific mathematician, very important. He is one of the mathematicians of Mount Olympus, right? He's almost unreal as a human being because in the olden times, he was very prolific, even into his old age. Which was very rare for mathematicians. Most mathematicians made their greatest contributions when they were very young, late teens, early 20s. Yeah, even the real advanced mathematics that we're using these days was invented by kids hundreds of years ago, believe it or not. So the idea that, you know, children can't be good at math is false. Now, Euler is very different in that even as an old man, he was cranking out theorem after theorems, and not just random theorems, things that we use and are very important, right? Math people, when we're talking, we talk about, oh, I'm going to use Euler's formula or use Euler's theorem over here or use Euler's method. And often at that level, it's like, which one, dude? Like there's so many things that this guy did, okay? Now, how did it come about? Euler considered this situation. Okay. So we're talking about compound interest. He was imagining this ideal compound interest scenario. So you deposit $1 in an account that earns 100% interest rate. Per year, right? Compounded. And it's compounded in a way that we mentioned. Compounded continuously is the phrase. We'll talk about this again in chapter 3, so don't worry about it. Right now, I'll just kind of slightly describe how the idea. So remember, interest I mentioned, we kind of added on at the end of the year, right? You keep money in an account. At the end of the year, they look at the balance in your account and they hit you with interest on top of that, right? So we take a certain percentage of this and we'll add that to the account, right? So that's called compounded once per year. Sometimes you can get compounded several times per year, right? So maybe like after 6 months, they'll look at your balance, they give you interest, and then that grows more. And at the end of the year, they look again and they give you interest. So that's compounded twice per year. So it compounded a certain number of times per year is just describing how many times you're being given interest. Compounded continuously means you're being paid interest continuously, meaning effectively an infinite number of times per year. Every second, every half a second, every millionth of a second, we're paying you interest on the current balance, right? We're consistently, continuously giving you interest, right? So that's what compounding continuously means. It's essentially an ideal scenario of paying interest an infinite number of times per year. This cannot, of course, happen in reality, but it's a very important conceptual thing. It pretty much can tell you what the worst case scenario is or the best case scenario is. You'll know this is the most we could ever make. We'll never make beyond this, no matter what happens in the world. This is the boundary, right? So you can't really go higher than this. Okay, so now the question is, how much money would you have at the end of 1 year? Okay. Now, based on what I was saying yesterday, and I was talking about, oh, how exponential functions behave in terms of polynomials, because like, look at that red line. Shoo! Like, dude, credit cards would charge you interest typically somewhere for the person with average credit between 18 and 22%, compounded once per day. Right, so that's how people get in trouble with credit card debt. It sneaks up on them. It's not always because of financial immaturity. The math says that the credit card companies, they know what they're doing. And it starts out, oh, you have to pay a minimum of $35, and oh, we hit you with interest this month, and it's $12 interest, and people are like, oh, that's not so bad. I'll charge something else, but they don't realize that eventually it's going to get bad. It really sneaks up on you. So understanding that and how that can get under control, and what you know about exponential functions, then they grow crazy fast. You might think, wow, 100% interest compounded an infinity amount of times. I'm going to have infinity dollars, right? The answer is no, you would not have infinity dollars. And Euler figured this out. The answer, how much money would you have under these really extreme conditions, is E dollars. You'd have roughly $2.72 at the end of 1 year. Now, if you keep going beyond that, of course, it's going to get huge. But like I said, sometimes exponentials, they take a while to start shooting off. At the end of 1 year, under these extreme conditions, you'd get about $2.72 or 2.7182 dollars, right? And Euler figured that out, and he tracked this number to very high precision. And it turns out this turned out to be a very important number beyond this financial context. Right? If it was just like, oh yeah, in this context, this number would just be known as 2.72 and we would move on. We named it a letter because it shows up all over the place, and we just want everyone to just be able to write a symbol. Just like how pi shows up all over the place and you just want people to write the symbol. Shows up in calculus. A lot of the things we know about calculus, we know because of this number. And a lot of the things we know about math today, we either would not know them, or it would be a lot more complicated if we didn't know about the existence of this number. So it's a very important number. Some people think it's the most important number in all of this function is the most important function in all of mathematics, because we use it. We get so much mileage out of it in all areas of math. So that's where that number comes from, and that's the natural exponential. We will talk about it a little bit more later. Right now, I want to start talking about that inverse function that we mentioned, logarithms. Okay, so let's start with the definition. The logarithm, and yes, I can say the logarithm. It turns out when we learn what the function for a logarithm is, what the graph looks like, it turns out it's 1-to-1, so there's only one output for each input. So for a certain input, there is the answer. There's no several answers, right? So the logarithm. of a number, should say positive number, and I'll talk about that later, to a given base. And of course, we also always assume the base is positive as well, is the power, i.e. exponent. So the logarithm is the power, right? It's that variable in the power that we want to solve for, that the base must be raised to give the number. So let's actually get more to notation. Logarithm, I write log, short for log. Base is a number that we put down here, a little number, and then we write the number beside the log, and that is equal to, this is the power, right? So this means, the base raised to this power will give me this number, right? So for example, if I ask you, what is log to the base 2 of 8? What would you say? Go, this is, go, give me a guess.
Would it be 3?
It would be 3, right? Since if I take the base 2 to the power 3, I get the number 8. Yeah, right? So you guys get it. So in some sense, this equation is equivalent to that equation. A lot of people are more comfortable and familiar with this equation, but it turns out that this equation is also pretty useful. And it's not that we just want to make math harder for no reason and introduce new notations. There's actually a reasoning for why we need this. It's kind of like we know about addition. Now we need to know about what subtraction means, right? We need to know how to undo addition. So it's like if we didn't know about this, it would almost be like we know how to add stuff, but we don't know how to subtract stuff. It's very important, not only conceptually for those reasons, but actually computationally and with the things we can get done. So logarithms have their own laws, of course. This is math, not anarchy. So just like there are laws of exponents, there are laws of logarithms. There are certain ways that they behave and function under mathematical operations, and we need to know what these ways are. So the first law is actually just going to be me writing the definition in math symbols or more general math symbols. Basically it says log to the base a of b equals c means a raised to the c equals b. These are two equivalent situations. And I really feel like I'm writing legal here. These are two equivalent expressions, right? So writing the equation on the left is exactly the same as writing the equation on the right. The difference is the equation on the right had the c up here in the top, while the equation on the left has the c down here isolated, right? So if I want to know what does c equal to, the logarithm is going to be the thing that tells me, right? In general, there are some other ways for very nice situations, but the logarithm is a general tool, right? So that's what a logarithm does. Now, it turns out by inventing this notation, a lot of other nice properties fall from heaven. For example, if I take log of something to a power, I'm allowed to take that power and move it down and multiply the logarithm. If I take logarithm of a product, I can actually split this up into a sum of logarithms. If I have logarithm of a division, I can actually split this up into a subtraction of logarithms. And at this point, I would like to turn your attention to something that hopefully, something that's very analogous and somewhat poetic, probably. is that, remember, logarithms are powers. This is what we mentioned before. And I want you to understand what these rules are implying. Remember how in the laws of exponents, we saw that, well, if I have some to an exponent and raise it to another exponent, we multiply the exponents, right? If I multiply two things of the same base, I add the powers. If I divide two things with the same base, I subtract the powers. Basically, what was happening in the powers, we now have it happening down on Earth. The logarithm actually takes those things that were happening in the powers and make it a main part of the show, right? Another thing that is useful about logarithms is that you will notice that the right side is computationally easier than the left side. Multiplying by a number is easier than raising to that power. Adding two things is easier than multiplying two things. Subtracting two things is easier than dividing two things. It really simplifies our operations and it really brings things down, right? So we can essentially go from an exponential situation to a polynomial situation, to a multiplication situation. And so now what happens is when things were crazy like this, we now brought them down like this and we can analyze them better. And this is why a lot of times when you're analyzing financial data or like stock prices and stuff like that and returns on stocks, you would analyze the log returns, right? Because the stock itself is volatile. When you hit it with a log, you calm it down a bit and you can analyze better. And a lot of times your science friends studying chemistry or biology or anything, and they're studying something on a long time scale, like some radioactive decay or whatever, they'll often do a log plot, right? And that's just take the time and squish it down, right? So a million years is now like at the 1.1 inch mark on their graph, right? So it really brings things down, right? And logarithms are very useful for those computational reasons. And in fact, logarithms saves lives. They were actually invented by this guy called Napier for the purposes of nautical navigation. Way back in the day, people would go out to sea and never return, right? It was very hard navigating by sea. We did not have Google and GPS back then. So it turns out it's just because it was such vast distances. We couldn't really, you're off by a very small angle and you end up way off your target. And so what we do is we want to figure out a way to not have these large expansions. And so we invented the operation, or Napier invented the operation of the logarithm. And they rewrote nautical navigations in terms of logarithms. And it literally saved lives. People would come home more often when they went out to sea. So that's the idea behind a logarithm. It's a way to know the inverse operation of an exponential, but it's also useful in taming down the aggressiveness of calculations or functions that you're looking at, which makes them very useful in a lot of contexts, including business and finance. So there are a lot of times when you're going to be in your finance classes, they're talking about log stuff and you're going to like, why are they using log stuff? You're just making things complicated. No, there's a very good reasons for it. There is another important thing. It's called the change of base formula. So this is a formula that's giving a name. Sometimes you're hitting things with logarithms to make things easier, but the base that was used is not really convenient for you. So sometimes you want to change the base, and it turns out we have a formula that allows us to change the base. I can change the base to some other base C using this formula. C is a convenient base to work with. Okay. Of course, here your A is greater than 0. It's not equal to 1. We'll see why it shouldn't be equal to 1 in a little bit. Right? So I asked you a question earlier. What is log to the base 2 of 8? Let me ask you a very similar question. What is log to the base 4 of 8? What do you think? Any ideas?
Is it 3 over 2?
It's 3/2. Good guess. Now, the average person is going to be like, okay, so I know the log is the power I have to raise the base to get the number. So 4 to the 1 power is 4. Okay, so that's less than 8. That's not what I want. Next number, 4 to the second power is 16. Wow, I overshot the answer. So I know the answer is somewhere between 1 and 2. Now, the question is, because I know it's not a straight line, it curves, the question is, well, is it exactly halfway between 1 and 2? Maybe it's 1.25. Maybe it's 1 and 1.75. Maybe is it 1.5, which is 3/2? It's not always as clear until you actually check it. However, we could actually get to a more clearer situation by just changing the base. You see, 4 is just not a convenient base to talk about the number 8 in terms of. What base would be more convenient?
2.
2, right? I know how to express 4 in base 2 very easily with an integer power. I know how to express 8 in base 2 very easily with an integer power. So 4 is just a weird thing to work with. So what I can do is I can introduce a base 2 using this change of base formula. Now, what is log of base 2, log to the base 2 of 8? Well, it's 3 because I have to raise 2 to the power 3 to get 8. What is log to the base 2 of 4? Well, it's 2 because I have to raise 2 to the power 2 to get 4. Right? So now the answer of 3/2 is quote unquote obvious, right? Based on this formula. And we can check that this is the case. Right? Take 4 to the 3/2. Do I get 8? Well, we learned from the laws of exponents yesterday that this is really another way of writing the square root of 4 cubed. That's 2 cubed. That's 8. So yeah, that's the answer. 3/2 is the number. Now, you might not be able to have guessed that at the beginning because we were working in base 2. We were working in base 4, which is just kind of weird, right? And yeah, we want to be able to change that situation. So the change of base formula is very useful for that. And I guess I'll talk about that in a little bit. I'm going to recommend that you memorize the first 5 rules. To just put this out there, I'm not going to ask you to memorize formulas all the time. There are times when I will give you the formulas, like I'll give you a formula sheet. But you shouldn't let everything be on a formula sheet. There are some things that you should know off the top of your head. So every now and then I'll ask you to memorize a few formulas, even though I'm not going to make that the thing. And there are some very good reasons for this, which I'm sure throughout the semester we will get to that. But just rest assured, I'm never going to ask you to do anything where there isn't a reason or there isn't an end goal. I'm not a random kind of guy. So you might not know, why do I have to memorize this? But there's a method to the madness. The following formulas, though, I'm going to give you like 10 rules in general, but memorizing the first 5, non-negotiable. You need to know them. The following, though, it's optional, but I would say it's highly recommended that you memorize them. Or even better, if you do enough problems with exponentials and logarithms, you'll kind of get to memorize these guys automatically because they're very useful to know as rules of thumbs. They will come up very often. So if you're studying correctly, you'll memorize them automatically. So you can even use them as a gauge for how well your studying is going. If you do a bunch of problems on exponentials and logarithms, but you don't remember the following 5 rules, means you probably didn't study enough. The following it is highly recommended that you memorize the following. So in my calculus classes, we're also starting out talking about exponentials and logarithms. So I'm doing essentially the same stuff in my calculus class at the moment. So among other things, one thing you can do is to know all these rules so well that you go find one of my students or one of the other students doing exponentials and logarithms in calculus, and you can just show off on them and flex that you know what, you don't know this. Just like to quiz your friend. Yeah, it'll help them study harder. So everyone wins. You have fun picking on them, and they'll go study hard because they're like, I can't let my friend who's in business beat me on the science stuff. Come on. So here's one. Log of 1, what is that? Turns out it is 0. Why? A raised to the 0 is 1. That was a exponential rule, right? So if you know what a logarithm is, you can figure this out, which is why I say you don't technically have to memorize it. If you really understand logarithms, the answer is obvious, quote unquote. But it's just nice to know. Log of 1 is always 0, right? You don't have to think about it. Log of 1 is 0. Log of 0, turns out it is undefined. Why? Well, think about it. I give you a positive number, say 2. What power do you have to raise it to in order to get 0? Well, if I raise 2 to a positive power, it's going to be positive. If I raise it to a negative power, well, it just means 1 over 2 to the positive power, so it's still positive. If I raise it to 0, I get 1. So whether I raise it to a negative number, 0, or a positive number, I always get a positive result. There will never be a situation where I actually get 0 as the answer. There will also never be a situation where I get a negative number as the answer. So that we can actually expand on this. In fact, log to the base a of x is undefined for x less than or equal to 0. You can never take the log of something negative. You can also never take the log of something 0. And again, if you fully understand what a logarithm is, how it works, that would be obvious, but it's just nice to know. Log of 0 means something bad happened. That can't happen. It's undefined. 8. Now, this is what is especially important for us. And again, it's going to be somewhat obvious after I write the answer down. Log to the base a of a to the x is x. Why? Because I have to raise a to the x power in order to get a to the x power, right? It's just like straightforward from the definition. This one is a little less obvious. It's not very hard to prove, but it's a little, you can't really at a glance have like this little sentence in your head for why it's true. But that is also true. Meaning if I have a base a and in the power I put a logarithm to the base a, then I just get the thing that's inside the log. Essentially what I want you to appreciate here is that when you plug an exponential into a logarithm, it's almost as if the log and the exponential cancel each other. And when I plug in a logarithm into an exponential, it's almost as if these guys cancel each other and I get the original input, right? So that's what we are concerned about, how we want to solve for the variable x that's in a power if I'm in a certain situation. Sorry, my screen spazzed out here, right? So like here, if I'm in this situation, which is like the compound interest formula, I have something raised to the power and I care about the power. If I want to solve for that power, this rule is what tells me, oh, I should throw it inside a logarithm. That's going to get me the power, right? So this is the subtraction to our addition if exponentiation took over the role of addition, right? So it's very important, right? So this shows y equals log to the base a of x is, and y equals a to the x are inverse functions of each other. And so in these situations, we can use the log operation to cancel the exponential operation. And vice versa. So like I mentioned, a lot of times in finance, you'll hit things with a logarithm just so you can analyze them better. But of course, when you get the answer, that answer will be in the form of a logarithm. You'd want to be able to go back to what the actual values are. And so that tells you that you're going to hit it with an exponential. So anytime you have any finance programs that are analyzing stocks, you should be aware that what the program is doing a lot of the times is it's taking the data, it's taking the logarithm of the data, it's analyzing that, then it converts the answer back to something meaningful by taking an exponential, and then it prints that answer on the screen for the financial analyst to go, okay, click next, right? Now, the 10th thing I want you to know about, it's more of a notational thing, it's not really a rule. So I spoke about the natural exponential and the number e. So it turns out a lot of times log to the base e is going to be a very convenient thing to compute. Not for you guys. For business and finance and engineering, log to the base 10 is the guy that you guys use most of the time. But a lot of the rules you guys use was invented by mathematicians, and mathematicians use base e. That's how we figure out a lot of formulas in the simplest way possible. So sometimes people take an alternative notation for that. They call it ln, and it's called the natural log. So if I write ln, it means base e. If we just write log, log of x, without saying what the base is, it really means log to the base 10. Or maybe I should have written it the other way. If we mean to say log to the base 10, we'll simply just write log x, and we will neglect writing the base. So ln, if you see ln, it's just a logarithm. All the rules of logarithm apply. It's just that the base is assumed to be the number e. Okay. Now, what I want to do now is I want to have you guys work on some problems for a little bit. Now, of course, we're not going to get through all of them now, but I want to split you guys up into groups, have you guys start working on the problems. You guys will come back. You'll tell me the answers that you got, and we will verify those answers next class. We'll work through these examples. But I actually want you guys thinking about it already. Okay. So you're going to have to know your laws of exponents as well as the laws of logarithms. And yeah. So 1, 2, 3, 4. How many people do we have? Okay, this is a little ambitious because we don't have that many people in this class. So I will say, can I get 3 groups out of this? Okay. Group 1. Two, group 3. Okay. So here's the plan. Actually, maybe like take a picture of that or something. Because I'm going to move you guys to another room, so you're probably not going to see the problems. So maybe just take a picture. And I don't know who's going to be in what group yet, so maybe I should actually tell you. There are going to be 2 to 3 people per room. Okay, so I just randomly do it. And as I mentioned, I'll be putting you guys into groups later in the class, later in the semester. This is not that. This is just for now. I'm just randomly putting you guys into groups so guys can talk to each other. So Cullen, Kathleen, and Stephen, you're in group 1. So take a picture of that or write those problems down quickly. Sophia and Tommy, group 2. Nahil and Taj, group 3. So here's the plan. We're going to do about 5 minutes. So here's what I would like you to accomplish in those 5 minutes. In the first minute, I would like you to exchange contact information. And there are only a few of you per group, so that shouldn't take too long. You know, just each of you type your emails in the chat or phone numbers in the chat, set up a WhatsApp group or something. I don't know if you guys are in the same cohort, but I want you guys to actually start getting to know others in the class. So that's the first minute. For the other 4 minutes, just start working on these problems together, get as far as you can. And then at the end of those minutes, I'm going to actually pull you guys back. You guys are going to tell me what your guesses for the answers are, and then I'll let you guys go, and we'll actually see how well you do. Don't use a calculator. I want you to actually do this by hand, just to play with the rules a little bit. So that's it. So,
Professor?
Yes?
I have class like right after this class. I don't have a break in between, so I don't think I could stay 5 minutes after.
Okay, stay as long as possible, but at least exchange contact information.
Okay, sounds good.
Okay.
Thank you.
Contribute as much as you can, but at least a few minutes. I'll give you guys a max of 5 minutes or something like that. Okay, so all rooms are open. You should see like an invitation pop up on your screen. Head into there, and I'll pull you guys back in a few. And I guess I can stop recording, so I'll see you guys back in a few. Okay, and we're back. So did you guys get anywhere? Are there any guesses? Did we solve any? Wasn't enough time? That's cool. Okay, so remember your group members. Hopefully you got into contact with them, and I'd like you guys to work on it together over the weekend. You don't have any homework due anytime soon, so I think it's fine. And the homework starts with chapter 3 anyway, not chapter 2. We need this stuff for chapter 3, but there's no homework on it. So this weekend, just work on this, try to get familiar with it. And next class we'll start by, I'll ask for your guesses, and you guys can tell me, and then we'll work through it. And hopefully we can get through everything, and we'll move on to the next section. So with that being said, thank you for your attention, and I think I'll let you guys go. So without further ado, I'll see you guys in the next one. Ciao.